Okay, I know you're in here. There you are. All right. Keep them coming. Okay. All right, we are now recording. Let's start from current slide, and we'll pick up and go from there. I can't think of any new news except, as already mentioned, I will be giving you the test today, so don't leave. If you have to leave early, get the test before you go. Okay. Any questions on anything we've done up till now? Okay. And this, in doing the test, let me go over this. Most of the time I make out my test in WordPerfect because I find the equation editor is so much more convenient to use, it's just so easy. And this one, the one that I was going from, just happened to be in Word, so I had to use Word's equation editor, and hopefully I didn't make any mistakes with it. It's such an awkward package. I mean, it's okay. They copied as much as they could from WordPerfect, but they just couldn't get it all right. So I'm sorry, I'm not a big Microsoft fan, if you may have noticed. Okay. All right, so we're still doing applications of integration. The last one we're looking at is fluid pressure and fluid force. Okay? And the objective is that one, find the fluid pressure and fluid force. Okay? Now, it's good to keep in mind, and I find if I were to classify myself, especially as a physicist, I'm very much a dimensional person. Okay? I think in terms of dimensions, not in terms of formulas and stuff. I've matched the formulas to make the dimensions come out right. So I do what I guess is called dimensional analysis. Pressure is defined as the force per unit area over the surface of the body. And what I mean by that is I think in terms of what is a common pressure that you would likely be measuring, possibly. Tire pressure? Yes. What's that usually measured in? Yes. What does PSI stand for? Pounds per square inch. Force, pounds per unit area, square inch. So I think PSI, pounds per square inch, that's what the pressure is. Okay? Force per unit area. Okay? So I think in terms of units, basically. In general, the pressure is proportional to the depth of the object in the fluid. So there is just about an equation, what they call a proportionality, and that pressure, and let's see, this book uses capital P for pressure. I always have to check to see. Pressure is proportional to depth, okay? And they use H for depth, which is sort of bizarre because most of the time we think of H as height, but H is also depth, okay, of the object in the fluid. Well, what is that proportionality constant? Well, that is the weight density. So then you can change the proportionality to P is equal to the weight density times the height. Okay? And again, thinking in terms of units. Weight density, and this is, I usually think of little w as weight, not weight density. So this may throw me some, but hopefully hang with me and correct me when I mess that up. Brandon, right?
Davis.
I'm sorry?
Davis.
One more time.
Davis.
Davis, got it. David Warren, right? Yeah. Davis Warren. I can't read my writing. Okay. All right. Anyone else sneak in while I wasn't looking? Okay. So this will throw me off because I think of W as representing weight. This is weight density. Okay? Weight density meaning, and again, density is, a weight density would be weight per unit volume. Okay? So weight per unit volume, which is three-dimensional, length times length times length, multiplied by length, which is your depth, that gives you weight per, or force per unit area, and that's exactly what pressure is. So I think of these formulas in terms of that. This would be the weight density, which is weight per unit volume. Now, most of the time we don't deal with weight densities, especially in the SI units. you deal with mass density. And how do you get from mass to weight? Have y'all had physics yet?
Times
Say again?
You may have said right. What did you say?
times the force of gravity.
Yeah, the acceleration due to gravity, exactly. Mass times acceleration, which in this case the acceleration due to gravity, that would give you. So the way I'm used to seeing this is pressure is equal to rho, which is the mass density, GH. And so that's the other form. Weight density, they're using WH, which means Ws.
Weight density, exactly?
Weight density is force per unit area, per unit volume. Okay, pounds per cubic feet. See, in the U.S. customary, we don't use mass at all. I mean, there is a unit for it. Any of you know that unit? In U.S. customary, no one uses it.
Right?
Huh?
You told us last time.
Oh, did I? Yeah. No one uses it. Slug. Yeah. Okay. When's the last time you wanted to buy a slug of potatoes? And never. Okay. But you buy a kilogram of potatoes, or whatever. But we do. We talk in terms of forces, not masses. So weight density is force per unit volume, weight per unit volume. Okay, pounds per cubic feet, or something like that. Okay. Here are some of the common weight densities of fluids in pounds per cubic feet. See this? Unbelievable. This author is living in the U.S. customary world, okay, which may be where we live too. By the way, there is a guy featured on the page here before I turn the page, Blaise Pascal, known for many, many things in math, in physics, and I guess you would include in math statistics. Okay, he's all over the place, well known for his work in many areas of mathematics and physics, also for his influence on Leibniz. Now, I didn't realize that. Although much of Pascal's work in calculus was intuitive and lacked the rigor of modern mathematics, he nevertheless anticipated many of the resulting important results. So he was a big influence in Leibniz. I was thinking Leibniz came before this, but I may have my dates mixed up. But what are some things you think of when you think of Pascal? Yeah, Pascal's triangle. That's used in the binomial expansion, okay, which is very much a math thing, but it's used all over the place in statistics. And if I'm not remembering wrongly, it seems like Pascal and a couple of the others were big gamblers. So they really got in statistics so they could have a leg up in gambling, okay? I'm sure that wasn't the reason, but they brilliant, brilliant mathematicians. How about in physics? Where is Pascal fairly well known? Yes, the unit Pascal, which is a unit of pressure, is named after Pascal. And it's, let's see if I can, it's a very, very small unit. It's,
isn't it just like a PM like that?
That's the rho, and that's usually they use for density. Oh no, Pascal is PA. PA, that's the unit PA. It's a Newton per cubic meter. Weight, is that right? No, per square meter. Newton per square meter. Yeah, I just said. Pressure is Newton per square meter. It's force per unit area. Well, a Newton's a fairly small force. A pound's bigger than a Newton. But think about a square meter is basically, look at that door, and from the doorknob down, that's approximately a square meter, maybe a little bit less. Whereas a square foot is, that by that, it's a pretty small unit. So it's a smaller numerator, bigger denominator. That makes a Pascal very, very small. If someone were to close the door there, the pressure would probably go up by several Pascal. Did anyone ear pop when that happened? No. Okay, so it's very small. So what's the equivalent on your tires to PSI? You know, there's usually in parentheses. Nowadays they put this one in thing and put the PSI in parentheses. Kilopascals. Yeah, KPA. Yeah. So that's it. It's such a small unit, they usually use kilopascals for many things. So here are some of the common weight densities of fluids in pounds per cubic feet. Ethyl alcohol, not that you would need to know that, 49.4. Gasoline between 41 and 43 usually, depending on the grade and what else is in it. Glycerin, 78.6. Sort of surprised it's that high. Kerosene, 51.2. That's another distillate. Mercury, goodness gracious. And by the way, mercury is a fluid at normal temperatures and pressure, the only metal like that, and that's 849 pounds per cubic foot. I'm so not used to using those terms for it. Seawater, 64, whereas freshwater is 62.4. This is the only one that I'm usually vaguely familiar with. Measure everything by that. Alcohol, of course, is less dense, gasoline less dense, glycerin denser, kerosene less dense, and so what difference does that make? Alcohol, gasoline, kerosene all float on water. Okay, so if you have oils, all your oils too. If you have an oil spill, then all that's going to come to the surface and choke out things underneath. You know, keep oxygen from happening there. So that's one reason oil spills are so bad, especially if the oil spill is associated with the fire, as in back in World War II and stuff like this, when the ship was blown up or something like that, and there was fuel in the water and there was fire. Many people, if they didn't drown, they were burned to death when they tried to come to the surface, and they were coated with fuel and caught on fire. So, pretty bad situation. How about the difference in these two? What ramifications do you get from that? Saltwater being a little denser than freshwater.
Saltwater is pretty salty in the water.
That what?
At the lower elevation, the saltier the water is.
Yeah, that certainly could be the case. Of course, the more compressed the water is too. So, but what I was thinking in terms of the plane in freshwater or saltwater.
Float more in
No, in saltwater. Yeah, float better in saltwater.
That's why the Dead Sea, right?
What's that?
The Dead Sea. That you floated in the Dead Sea.
Yeah. The Dead Sea, you can hardly sink. I think they say it's so saline, such high concentration. It's way more than this, okay? And yeah, and even Salt Lake, they say it's really hard to go under the water there, because that's even, but seawater, you float better and more easily. And I don't know if you've noticed, say again?
If you walk on record,
Walk on what?
if you get a lake of record, you can just walk on it.
Yeah, you would float for sure, but you wouldn't want to do that long because it's pretty toxic and can actually go through. But actually, lead will float on mercury. That's that dense, okay? So it's pretty incredible. I don't know if y'all are familiar with vessels that go both in freshwater and saltwater, like, you know, go into estuaries and maybe up rivers for a little ways or something, but also go out to sea. You know, small craft. They'll have two water lines because when they're in saltwater they sit higher, freshwater they sit deeper. Okay. But anyway, that's some of the common ones. One sort of interesting, there is actually one planet that is less dense than water. So if you had enough water, it would float. Okay. Saturn, by the way, is less dense than water. The gas giants are pretty close, but it's the lightest of the gas giants, or less dense of the gas giants. Okay. When calculating fluid pressure, you can, there's another place, and this is why they brought them up. You can use an important physical law called Pascal's principle, named after the French mathematician and physicist Blaise Pascal. Pascal's principle states that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. Okay? For example, in this figure, 765, the pressure at the indicated depth is the same for all three objects. So if you have a plate that is flat, the pressure is the same as it is on that portion of a vertical plate or on that same portion of a slanted plate. The pressure at any depth is the same no matter the surface. Okay? At that depth. Okay? So, with that in mind, that helps us to be able to come up with a way to calculate those pressures. Because fluid pressure is given in terms of force per unit area, pressure, PSI, force per unit area, the fluid force on a submerged horizontal surface of area A is pressure times area. Because this is force per unit area, multiply that by area and you get force. Pressure times area equals force. So if that's what you're looking for, finding either finding the fluid force, you do force times area, pressure times area. So here's example 1. Find the fluid force, hard to say too fast, on a rectangular metal sheet measuring 3 feet by 4 feet, but this one's going to be horizontal, that is submerged in 6 feet of water, is shown here. Here is your sheet, 3 feet by 4 feet, okay, horizontal, and we want the pressure of it. Okay. Corbin? Yeah. All right. So, don't believe much calculus is going to be involved in this one. Under fluid force, yeah. Submerged in 6 feet of water. Okay, that's what we got. Okay, so what would that fluid force be? What was force? Pressure times area, because pressure is in force per unit area times area. What is the pressure? We gave it earlier. Weight density times depth. They use H, but it's a depth. Okay, and what's area? Length by width, right, of a rectangular sheet. So what would we have here? And let's say it's in water. So what's the weight density of water? 62.4. What units? Pounds per cubic foot. Okay, this SI units. I mean, U.S. customary units. Times the height. So what depth was it? 6 feet. Times the area. And what was the area? 12 times 12 what unit? Square feet. Exactly. Okay. So pull out a calculator, crank away. 62.4 times 72. By the way, the cubic feet cancels with feet squared times feet. That gives you pounds. So what's the total fluid force? Anyone got it? 62.4 times 72. Something on the order of 4,492.8. Is that what you said? Okay, that would be pounds. But in reality, you have not that many significant digits. Okay? So, at worst, and this isn't anywhere close either, I would say 4,493 pounds. That would be approximate. The best you could do would be 4,490 pounds. But in reality, you really probably couldn't do better than 1 or 2 significant digits. But I bet you the book gives them all, don't they? Yep, they get to. No way you can get 5 digits of precision out of something that the best precision you got was 3. There's 1. There's 2. There's there's no way. In fact, that 2 was just a 1 by 1. But I'm not going to say 4,000. That's stretching it a bit. There's no reason for a decimal in there. Okay. In reality, about 4390. 4,500 probably would be close enough precision-wise. Okay. But they put 4492.8. Okay. Now, horizontal sheets, very thin sheets, that's all you have to do. No calculus involved. Okay. Oh, and here's, they show it. Because the weight density, water 62.4 pounds per cubic foot. The sheet is submerged 6 feet of water. The pressure would be 62.4 times 6, 374.4 pounds per square foot, PSF, okay, and then multiply that the number of square feet times 12, and that gives you 4492.8. Too many significant digits. This result is independent of the size of the body of water or how deep it is or anything else. All it depends on is how deep the piece of metal is and what the doesn't even depend on the weight of the metal. It could be aluminum, it could be lead. The pressure is still the same. The fluid force is the same. It was in a swimming pool, a lake, whatever. Okay? Not the ocean, though. That would be a different. So, the definition of force exerted by a fluid. The force F exerted by a fluid of constant weight density, W. So this is assuming that your density isn't varying too much with depth. So in other words, you're not going too awfully deep, where you could get some density variation. Against a submerged vertical plate, not horizontal, but vertical, from y is equal to c to y is equal to d, usually that's going down here. Most of the time, down is negative. In this case, down is going to count as positive. So the force is the weight density, which is, we're assuming constant, times the limit as your partition is going to 0, of the summation of I to n, which is your partition is going to 0, n is going to infinity, of your depth, okay, at any place y sub I, okay, times L of y sub I. What in the world is that L? L is the horizontal length of that strip that is dy. So, frankly, you start with getting a strip which is delta y, finding the length of that strip and how deep that strip is. That then gives you length times depth times thickness. That's your cubic units, cubic feet, whatever. Multiply that by weight per cubic feet, and that's what gives you your weight per force. Okay? If you do the limit, then this is the height function as a depth of y, your length function as a depth of y, and that could be constant, by the way, and your dy. And you're integrating from c to d, where c is at the top limit underneath the water to d at the bottom. Okay? Where h of y is the depth of the fluid at any strip, dy strip there, y. And L is the horizontal length. So if you have a odd-shaped length, then you integrate that as well with respect to W. So here is an odd-shaped plate. Vertical gate in the dam has the shape of an isosceles trapezoid. Now what do we mean by isosceles trapezoid? Iso means same. So and obviously your top and your bottom of the trapezoid are never the same, okay, by definition. So it's the lateral sides that are the same here, okay? So it's an isosceles trapezoid, which means the angles are also the same. It's isosceles. Trapezoid, 8 feet across at the top, 6 feet across at the bottom, with a height of 5 feet, okay? That's height, that's not the lateral length, it's the height. So what is the fluid force on the gate when the top of the gate is 4 feet below the surface of the water? The fluid force on that gate. Okay? Now, at least help me set up things here. Well, what are we going to use for our integrating variable? What you reckon? Your integrating unit. Doesn't it make sense to do a dy, a delta y thickness? So this is your, I like to think in dy's. Technically, if it's a thickness, it's a delta y, but I think in terms of dy. Okay? Now, what is the depth of that? Now, we're using h for depth, which seems kind of crazy. Okay? And why is that depth, isn't it? Okay, how deep it is. So your integral, if you're doing dy, and I like to, maybe thinking backwards here, here's a dy. So obviously you're going from 4 is the minimum depth to 4 plus 5 is 9 is the maximum depth, right? So go on and get these easy things done, okay? Your dy is the thickness of that plate. What you need to do is now deal about the length of the plate. Yes?
Why can't you just do 4 plus half of 5?
4 plus half of 5.
And then wouldn't that give you the dy? Or like give you...
Well, I may have drawn it close to half, but that strip could have been down here or up here or anywhere. Right, so it's varied. And we've got to get to that. What is our h as a function of y? Well, our h of y is going to be y, how deep you are. Okay? So there is one of the components here. H is just your y. Okay? That's how far down you are. Okay? Going from 4 to 9. That limits you. You don't count this up here or anything down here. Okay? So now all we're missing is that length thing. Okay? There's your depth, your thickness. You need to know this length. Okay? Now, doesn't it sort of seem like you're probably going to use some similar something and others here? Okay? And h is equal to 4, when h equal 4, your L, let's make it script L, is equal to 8, and when h is equal to 9, your L is equal to 6. Okay? So the length is decreasing by 2 every time you go down 5. So that's kind of a dl dy kind of is going to be 2 to 5, right? But it's going in the opposite direction, so minus 2 to 5. Okay? Does that make some sense there? So dl dh, with L being dependent on h, that would be minus 2 to 5. Would you buy that? So isn't that kind of like your slope? Right? Okay. And let's just, that's a slope, let's pick a point. Either one of those points should do, right? So L depends on H, so you'd have an L minus, which one you want to use? I really don't care much. Is it Brendan?
Yes, sir.
Huh?
Yes, sir.
Yeah, okay. still learning names and faces. After about 16 weeks, if I get you wrong, start throwing things at me.
Yes, sir.
Especially since it's a 10-week term. Okay, all right. Okay with that. All right. So, which point you want to use? 4 and 8 or 9 and 6? I don't really care too much. 4 and 8. So L minus 8 is equal to minus 2/5 H minus 4. Would you buy that? Okay. So L minus 8 is equal to minus 2/5 H plus 8/5. And then let's add and by the way, H is Y. So let's go back and make this Y. Is that all right? That is your depth, okay. Add 8 to both sides. Well, how many fifths is 8? 40 fifths. So this will be L is equal to minus 2/5 Y plus 40 fifths. Okay? Which you could say, make any more sense to do, L is equal to 1/5 times 40 minus 2y, or let's make it 2/5 20 minus 4y, 20 minus y. That be okay? Whoops, I need a minus sign in front of it. That's getting really, wait, if I reverse the order, I've already taken care of the minus sign, okay. I hope I haven't confused myself too badly there. I know I've probably confused you. Let me rewrite this as 2/5 20 minus y. Yuck, yuck, yuck. Okay. Let me clean that up. 2/5 times 20 minus y. Because it's all crowded in there. Okay. Let me make sure. They got 24 minus y. How did they do that? Or do they? Say that again.
On like 48, 75. Now when you have L equals negative 2 over 5y.
Okay.
48.
Oh, 48. That would make sense, wouldn't it? Yeah. Okay. 8 and 5 is not 40. I mean, 40 and 5 is not 40. Okay. That I don't know how that happened, but there it is. Okay. And this time we're factoring out a 2, and that would be a 24. Okay. That's perfect. Whoops, wrong one. 24 minus y. I can't write. 24 minus y. Okay. Except, okay, I was wrong. They're doing negative downward. I was doing it positive downward. Let's see if we get the same answer. Okay. I think we should. But let's just see. So this will be, we'll have the 2/5 out front. If you prefer it, do it the way the book did. And 24 minus y. Okay? Well, let's multiply that through before we do our integration. Okay, let me, can I erase these now? I think we've gotten all the use out of them. I can. Okay, so that would be 2/5 times the integral from 4 to 9 of 24y minus y squared dy. Okay. Ariel? I have a 50-50 chance on you because there's only 2 females in the class, and I've had Dakota before, so I should recognize her. Okay, I mean Nakoma. I have a Dakota in my last class and Nakoma in this class. Okay. So how do we integrate that? 2/5 times antiderivative of 24y. 12y squared, right? Minus y cubed over 3, evaluated from 4 to 9. Okay? I'm going to take this to the top of the next to do my calculations. I'm going to, yuck. Okay, 2/5 times, let's plug in the 9. And I'll need calculator help here. 81 times 12. Anyone do that in your head? I might be able to, but I sure don't feel like doing it today. 972 minus, yuck. Okay, I should be able to do this one in my head. 27, no, I'm sorry. Should be able to, but I doubt if I will. 81 times 3 would be 243. Okay. All right. Minus 12 times 16. Should be one that's in there, but it's not. 12 times 16. It's 144 plus 48. What is it? 192 minus 192, and then plus, because it's minus a minus, 64 thirds. Okay. All right. See what this turns out to be. We'll see how badly my going downward rather than upward is going to screw us up here. Okay. All right. Adding the positives, 972 plus 64 thirds, whatever that comes out to, subtracting the negatives, which is a 235 from that, and then multiplying by 0.4. Say that again. Oh boy, I really messed something up here. That is nowhere close. They get 13,000, and we're no way we're going to ever get the 13,000 out of that. So evidently, my choice was pretty poor. Okay, I don't know where I messed it up, but somewhere it definitely did. Let's go back and check this. 81 times 12 is sure enough 972. Yeah, that makes sense. Wow. Oh! Take the answer you just had, multiply it by 62.4. Sorry about that. I forgot that in there. That's our density. We haven't included. Say again?
13,935.
Point. So that rounds to 36. exactly what they got. Multiply that by your density, 62.4. That's what I forgot to do. 13,936 is what they rounded to pounds. Yeah, you can't get pounds out of it. What we were doing up to that was just volume. We didn't include the density anywhere in there. And that's a constant, so at the end, multiply with that. Okay. 62.4 was right there in the book all the time. Okay, so yeah, it works out the same way.
Does it matter whether or not that's positive or negative going down?
As long as you keep everything that way. Like if I'm going down from 4 to 6 and everything going down is positive, yeah, then this is perfectly fine. So the slope is going down, you know, everything has to be going down positive. So as long as you are consistent with that, yeah, it should come up the same. I was kind of surprised because I hadn't been talking in terms of that before, but they did everything with down being negative, which is fine. I mean, down is usually negative, so keep up with it. But that way your limits on the integral were from -9 to -4, but that meant your depth was minus y, you know, because it's negative. And to me, it's just harder to keep up with all those negatives than just have positive going down. I mean, it just sort of makes more sense that way. Okay. Let's see how they did it, because they do it. So setting up a mathematical model for this problem, you're at liberty to locate x and y axes in several different ways. A convenient approach is to let the y-axis bisect the gate at the place and the x-axis at the surface of the water, as shown here. So we kind of did that, except I just went surface of the water down, so I kind of bypassed all that. I didn't even mess with an x-axis at all. I guess I should have, but I didn't. Okay, let's see what they're saying. So the depth of the water at y feet is negative y, because y is negative going down and your depth is positive, so you have to have a negative y. Double negatives here drive me a little nuts. Okay, your h of y then would be minus y. We just made it y because we're going positive down. But then your depths are going from -4 to -9, which if you're integrating upward is from -9 to -4, which doesn't seem like it should be, but it is. Okay. To find the length of region, find the equation of the line forming the right side of the gate. So we'll find that and double it. Okay. So the equation of this line is a line that's going from between these 2 points. Your x, because this was 8 across here, this is 4. Because this is 6 across here, that is 3. The equation of that line would then be change of y was 5, and change of x was 1. So it's 5 over 1, and you double that, and you get 5 over 2. Well, so that's the equation of the line. L of y, and they just did that length there, and they came out with y minus 9, which is what we did, and then that's your slope of that line was 5 over 1, 5, x minus 3, going from the bottom of that, x minus 3, you're using 3 negative 9. So they did that. That came up with y plus 9 is equal to 5 times x minus 3. Or y is equal to 5x minus 0.4. Yeah, minus 27. No, minus 15 minus 9 is minus 24. Okay? Because that line passes through those 2 points, that's the equation of that line. Okay? Then solving that for x, because you want it in terms of y, that would be y plus 24 divided by 5. That's your x, and you have two of them, so double that, and that's what gives you 2/5 y plus 24. That's your length. I just feel like ours was a little easier to conceptualize than all these steps. This is not hard, but it's just kind of awkward. And finally, by integrating from -9 to -4, you can calculate the total force. I had forgotten to bring out my density in front. That's where I messed up. I was just doing the integral. And there's your integral 62.4 from -9 to -4 of negative y 2/5 y plus 24, which doesn't seem like any way in the world that would come up with the same thing ours did. Pull out the minus and then do that, and you wind up with a negative integral, and the negative sign up front makes it positive, and that gave you 13,936. So sure, this way is perfectly correct, and maybe in some senses more logical, maybe, but there it is. All right, let's move on to example 3, which they do not do. So let's try to get this one done fairly quickly. A circular observation window at a seawater aquarium has a radius of 1 foot. Okay? So here's your circular thing, and the radius here is 1 foot. Okay? So let's set up an axis going right through the center of that. So this would be 1, 1, minus 1, and minus 1. Okay? No, yeah, radius of 1 foot. Okay? The center of the window is 8 feet below the water level. So water is up here somewhere. That's not quite to scale, obviously. So this is the center is here 8 feet below water level. Okay? Shown in the figure. What is the fluid force on the window? And they just say water. Oh, it's seawater aquarium. Notice that word in there? Okay, you'll have to use seawater, the density of seawater. Okay? And you're wanting to know the fluid force on the window. Okay. Now again, in these kind of problems, you almost always need to take your dy like this. Okay. Now you want to do it the book's way of negatives or downwards, or you want to do it the way I did it before. Really doesn't matter. Just be consistent.
How we did it last time.
Like we did it last time? Okay. Well, we're going then, your y's are going to be going from 7 to 9, right? If that's your dy, and the y's are going from 7 to 9. Now we're counting downward as positive here, okay? A little hazardous, but doable, okay? This time though, and our depth is y, okay? Just like before. That's the nicest thing about this. Wherever you are, the depth is y, okay? Your dy takes care of the other part of it, and now we've got to figure out basically your L here, okay? Now, the radius is going from as you're going from 7 to 9, from here to here, your radius starts at 0, ends at 0, and halfway in between you're at 1. Okay? So, let's see, how is the best way to do this? you know here that any point on here, x squared, if this is x, now our y is coming from above, so the y here is 8 minus y, okay? This is your y here, right? And this length here is 8 minus y, right? So plus 8 minus y squared is equal to 1. Now, is that always going to be true? Let's do y is equal to 7 here, and your x is 0, obviously, and this will be 8 minus 1 is 1 squared is 1, so that works. Down here where you're at 9, 8 minus 9 is negative 1 squared, and this is 0 again, so that works. And here in the middle, where your x is 1, and 8 minus 8 is 0 squared, so that's 1. So it looks like that works for all these steps, doesn't it? Okay? And so what we're interested in is this is a function of y. So we want to solve this thing in terms of x equal, okay? That just gives you this length here. So you're going to want 2 of those. So we'll come back and double that in a minute. So x squared plus square that binomial, what you get? Not that hard. Square the binomial. 64 plus y squared is equal to 1. Okay, let's get that solved for x in terms of y. So it'd be x squared is equal to 16y minus y squared minus 63, right? Okay, so x is going to be the positive square root of that. Oops, that's a minus 63. I'm not liking this too much right now. Okay. And then I've got to double it. Okay. Boy, that stinks, doesn't it? I think that's our length, isn't it?
Why do you double it?
Because this is going from here to here, and our length is here to, all the way across. Is that right? Does that feel okay? Okay. So, I think it'll work out okay. Let's combine the 2 with the y that we already had there. The square root of 16y minus y squared minus 63 here. And we're going to multiply that this time by 64, because this is the density of seawater, right? And everything's in feet, right? Yeah. 8 feet. Okay. Our density is 64. Yeah, 64 seawater. Okay. Now, the good news here, I think, is how can we integrate that thing? I don't know if this is good news yet or not, but I'm hoping it will be. What would you try? Second? Okay. What would be your, oh wait, let's see. Yeah, y'all have done substitution, haven't you? Okay, does that ring a bell then? What would you substitute? Okay, yeah, that's what I was going to say. The inside part of the most complicated part of the problem, that'd be 16y minus y squared minus 63. Then du is equal to minus 2y, done, dy, okay? Now, I see a 2y dy right there. That's why I wanted to put the 2 with the y there, okay? But we got that problematic plus 16 and also a minus. So what would happen if we did, can we do this? Minus, I don't think we can do that. Okay. Oh boy, what a pain in the neck this is. So maybe this wasn't the best way to go. Okay, no it wasn't. Whoops, yuck. Didn't know my eraser was still on. Okay, I've lost everything here. Okay. Actually, and this is not a bad idea, let this be your XY, okay? That's your origin down here then. Then your Y is just Y, and that's much easier to deal with than that radical, okay? And then your depth, what we were calling Y, that's not your depth anymore. Your depth is, if this is Y going up here and down here and out, okay. Let's just start over. Sorry, I didn't mean to take this long with this problem. Okay. Okay, I don't need that anymore. Okay, here's your circle of radius 1. Okay, and this is the x-axis and the y-axis. All right, here's your depth of water up here, and this is 8 feet to here. Okay, those are 1 foot each, yeah. Okay. And again, what we did before was perfectly fine here, except now we don't have to worry with y minus something or another. Okay, and your depth here is from, if this is y, again this is your dy, not a bad place to start, dy. And your depth's going from -1 to 1. If doing it positive. Okay, now I'm doing positive, y is going positive upward. So I have to keep that in mind here. Okay, I think that'll just make more sense if you're down here. And your length is simply, and here's where your play comes in. What is the depth here? The depth here is 8 minus y. Every place, right? Here it would be 7, here it would be 8, and here it would be 9. Okay? So there's your depth. Your length, we did the square root of, let's go back to this. This is x, this is y, and this is the square root of x squared plus y squared, right? That's all that is there, because all the way around the circle that's going to work, okay? So let's fix that to be we want x is equal to okay, no, this is 1. Sorry about that. 1, that's 1. So x is equal to 1 minus y squared. Or x squared is equal to 1 minus y squared. Because that Pythagorean theorem, okay? And so therefore x is equal to the square root of 1 minus y squared. And that would then be, 2 of these would be 2x. That would be your length. So here we'd have a 2 in front and 1 minus y squared. Okay. I think that's our equation now. And I'm doing this so fast I may have messed up some of my signs on it, but let's see how it turns out. Here again, your let u equal 1 minus y squared. Du is equal to minus 2y dy, and there you have a minus 2y dy. So you have the integral minus 1 to 1 of 16 times the square root of 1 minus y squared dy minus 2y square root of 1 minus y squared dy. 2 different integrals here. Oops, let's keep it on this side. Now probably I should have stopped way back then. Trouble is, I don't think we've done anything that allows us to do that now. That's really a pain in the neck. This one we can do. Substitution is certainly going to work for us there. How do they deal with that here? Okay, this is how they deal with it. This right here is the area of a semicircle. That's how we do it. Without doing an integration there, which can be done, but not with any techniques we have so far. This is just simply the area of a semicircle. Okay? 16, take the 16 out of here, and you've got the area of the semicircle. And they go from there. And then this you can do by substitution. So we'll just, it gets a little hairy here, but it's really, we've already spent more than enough time on it. I wondered how in the world are they going to do that, but how they do it is not evaluate that integral to say it's area of a semicircle. Done. And so let's not do any more on that. You can look at it in the book and follow along and see the way they proceeded there, which is sort of cheating in my mind, but indeed it really is what they said. Let's look at homework exercises 7.7. Do either 3 or 5 or both Both of those are at calcchat.com. 3's at CalcView. Do number 7. That's just at CalcChat. Do any of the odds 9 through 13. They're all 3 at CalcView, but 13's at they're all 3 at CalcChat. 13's at CalcView. Do either 15 or 17. They're both at CalcChat. 15's at CalcView. Do either 19 or 21. They're both at CalcChat, neither at CalcView. And then 23, do 23, it's at CalcChat. And then they have exploring concepts. I don't know how much they have at CalcChat. You can look at 27, 25 if you'd like. 25 and 27 if you'd like. If they're at CalcChat, you can do a little bit more. If not, just think about them and move on. Do any of the odds 29 through 35. I'll let you choose which ones of those you want to do and go from there. Okay. There are review exercises at the end of the chapter. Those also, calcchat.com has odd number exercises, so I think the back of the book has all the answers to them. I'm not sure. Let me check. And I'm not absolutely certain mine's the same as yours, but I'm guessing it is. Let me just make sure that I'm not looking at an odd chapter, that I'm looking at the one we're really doing. This is chapter 7. Goodness gracious. Here we go. Review exercises is only odds. Okay, I thought they had them all. Okay. So any of the odds 1 through 9, either 11 or 13, and these are all at CalcChat. They're in the back of the book and at CalcChat. 15, 17, 19, 21, 23, 25, 27, 29, 31, any of the odds 33 through 39, and 47, 49, and or 51. I left off those with center of mass type things. All right, that finished chapter 7. So before I forget it, before any of you forget to tell me or whatever, let me go on and pass out, maybe just pass out or pass out your tests. Okay, and again, if there's any really weird looking stuff on it, it's because I had to use Microsoft Equation Editor rather than one I really prefer, WordPress. Okay. Each one text 1. Text 2. Each one in text 1. Before we get out of here. Each one is somewhere over there.
Do you mind if I get one for color?
What's that?
Do you mind if I get one for color?
Oh, I don't know. Okay, we are continuing. You do that, Patrick? You know we are continuing.
Are you going on 8?
Yeah.
Yeah, that's fine.
Okay. Yeah, I figure you must have to. Okay.
Can we get our bathroom break real quick?
What's that?
Can we get our bathroom break?
Oh, sure. That's a good time for that, I would say. Okay. I'll pause this. All right, for folks listening at home, if you didn't pick up on it, I've passed out the test for Chapter 7, and I'm right now about to give, and if you notice discrepancy on, inconsistency on margins or style or whatever, again, I was using Microsoft Word, and for some reason their number 2 would not allow me to set it up the same way I did 1 through 10, and I do not know why. I mean, it was just, if I moved the margin, tried to move this margin, it moved everything, and I fought with it, and I said, I'm quitting, I'm just going to let the margin be out of line. So, it's in line, but it's not set up the same way. But forgive me that. Okay, 1 and 2 are from section 1, this is 7.1. 3 and 4 are from section 2, 7.2. 5 and 6 are from 7.3. 7 and 8 are from 7.4. 9 is from 7.5. We didn't have any from 7.6, and 10 is from 7.7. I think. Okay.
What are 1 through 4 again?
What's that?
1 through 4.
1 and 2 are 7.1. 3 and 4 are 7.2. 5 and 6 are 7.3. 7 and 8 are 7.4. I think that's right. Let me make sure of this. And 9 is 7.5 and 10 is 7.7. I believe that's how I broke them down. I think you'll see as you do it, that's almost as it has to be. All right. Any questions? Chapter 7. Okay, let's get moving on chapter 8, which to me is probably one of the applications are important for sure, but these are techniques. This is sort of kind of the meat of the course right here. Techniques, integration techniques, and improper integrals. And I think I'm going to be a little less emphatic on the improper integrals and more so on the techniques. Okay. So let's look at some basic integration rules, which I think we've already talked about. Most of these, we'll review the procedures of fitting an integrand to one of the basic integration rules. Okay? And we're starting with fitting integrands to basic integration rules. Okay, so this is it. All right. These, you'll hardly have to say them at all. Okay? The integral of a constant times a function, an integrable function, is the constant times the integral of that integrable function. The integral of the sum or difference of two integrable functions is the sum or the difference of the integrals of those two integrable functions. Not that easy to say very rapidly. The integral of du is u, okay, plus c. Of course, any indefinite integral, you've got to have some constant of integration. Your power rule, and n can be any number in the world. Positive, negative, fractions, decimals, believe it or not, even irrationals, except it can't be minus 1, okay? The integral of u to the n du is u to the n plus 1 over n plus 1 plus c. Of course, the reason it can't be a minus 1 is then you would be divided by 0, which we don't want to do, okay? What if it is a minus 1? Then another way of writing that would be u to the minus 1 du, or du over u is simply the natural log of absolute value of u plus c. Now, again, the plus c can take any form you want to. Most of the time when I'm doing that, I would make that a log c, so therefore then I can combine those two things and be, it comes out a little nicer. Integral of e to u du, my favorite is e to u plus of c. Again, I would probably say that e to the c, and it makes it easier to deal with. Now, the integral of a raised to the uth power du. Don't know if you remember this from your rule of logarithms, but anyway, just precede that by 1 over log a, and it follows the same way. A to du. Integral of sine u du is minus cosine. Remember your differentiation integration rules, the signs change. The integral of cosine is sine. The reason for this is the derivative of cosine is minus sine, so that's why the minus is here. The derivative of sine is cosine, and that's why you don't have a minus. And the integral of tangent u, I don't know if you remember this, but from substitution, that would be minus the log of cosine u plus c. Now, that's not one I would say is worth remembering. There are other ways to express that. That's not my favorite, okay, but we'll move on from that. We'll probably get back to that. The integral of cosine, similar to this, cotangent, will be log of absolute value sine plus c. Integral of secant And again, these are ones I look up. I don't try to remember these. They're so easy to get crossed up, you know. And that's this and this. We'll be good. This one's easy because derivative of the tangent secant squared, the integral of secant squared is tangent plus it. Same thing here with the minus secant tangent, you know, because the derivative of secant is secant tangent. Those who follow from that. Now, this is not one I memorize. Okay? These three down here. I think we're going to see how to do these a little bit later. Okay? But here's what I do remember. From your Pythagorean identities, sine squared plus cosine squared is equal to 1. Okay? Well, if you then the sine would be the square root of 1 minus cosine squared. So, and vice versa. So, this is always going to be for a sine here. We're going to see how to do these so you don't have to memorize them. This is going to be your inverse sine or arc sine, because 1 plus tangent squared is secant squared. This is your tangent. You've got a 1 plus, no square roots involved. And this is the secant, and that one's just sort of weird. We'll see how to get that one a little bit later. At least I think so. Every other text shows you how to derive those rather than anything close to memorizing. Okay. But most of those are pretty straightforward. So let's do some integrals here. Okay? Now, we don't have to go back and use the table, but how would we go about, well, no, they're jumping right into it, aren't they? Okay? This one, the first one, you almost have to use a table. Okay? You don't quite, and I think I'll go on and show you the technique to use. I really hate it. I guess for now, let's just use a table, okay? From the three. What does that look like? I pointed it out when we did it, saying that you won't have to do this, and now we're having to do it. Because of tangent squared plus 1 is equal to secant squared. That's the key to remember this is an inverse tangent. I know that seems like it's a big stretch, but that's how I remember this. So this is an inverse tangent of something. Okay, let's go back to the table. The tables really, you need to know how to use them, so let's use them. That one's coming from this one right here, number 19. Okay? In this case, you got a 4 in the numerator, and what I'm going to do here is first take the 4 out of the numerator and make it dx over x squared plus 9. Is that okay? Okay? I went the wrong way. Okay? Now, well, they have the 9 in front, so let's just reverse those two. 9 plus x squared. Not that that matters any, but just to get it looking just like that. You agree those are equivalent, right? Okay? Now, what is your 9 here? What is it over here? A squared. Okay? So, if 9 is equal to a squared, what is a equal to? A is equal to 3. Okay? So let's go back to here and see what that is. Well, this first is equal to 4 times, and now we're going to get it straight out of the table. Oh, if I could go back. Okay. That would be 1 over a, which is 1 over 3. Right? arc tangent. I prefer inverse tangent just because it's easier to write, okay? Means the same thing. Of u over a, well, our u is their, our x is their u, so x over 3, okay? Plus c. Okay? So this will be, the answer is 4/3 inverse tangent of x over 3. Okay? Using the table. Later we'll see how to get it without using a table. Okay? But you need to know how to use a table. Okay? Now, how about this one? Would you use the same approach? Okay? This one, and most of you said you had done substitution. I know a couple of you have not. So I suggest let's use substitution in this one. Okay? And by the way, I don't think you'll find this back on the table. So what do you think you would substitute? Second? Let u equal x squared plus 9. If I can write. Okay, sorry. Then, what's always follows that? du is equal to 2x dx. Got it. Well, if I had that 2 on the outside, then I would have 2x dx. I like that over, well, I'm mixing them up here. Let me not do that yet. I'll change them on the next one. And this would be x squared plus 9. Okay? That would be 2 times the integral. Well, what is 2x dx? du over, and what's x squared plus 9? U is, x squared plus 9 is u, right? Okay? Now, what's the integral of du over u? Now, you can use a table if you want to, but after a while you should know this one pretty well. What is it? Natural log of u. And now go back and plug in what u is, or u are, and that is 2 times the natural log of x squared plus 9, right? That's what u is. What did I leave off? Okay, of course it's got a plus c. Only I'd probably do a log c, but not now. But what did I leave off that from the previous line? I asked for the value bars. Was that legal for me to leave them off? Why? Yes, x squared is always positive. We're dealing with real numbers now, remember? Real numbers, anytime you square it is positive, add 9 to a positive number, it's going to be more positive, okay? So therefore, we can lose the absolute value bars, okay? So that's the B part. How about the C part? What are we going to do with that one? Any ideas so far? Okay. I'm going to show you a little trick. Let's first factor out a 4. And that gives us our x squared over x squared plus 9 dx. Okay? Now, that looks a little similar to, but different from, what we had above, right? In B. So let's do, trying to think if I really want to do this way or not. Let's try it. Let's let. There's another way I really want to try, but I want to hold off on that for a bit. Let u equal x squared plus 9. Nope, this isn't going to work that way. Let me try something else. You know, nothing in the table they gave us is going to come close to that, is it? And there may be something really simple about it. Yeah. Okay. Well, yuck. Whoops. Okay. We're going to start with the integral there. Okay. 4x squared over x squared plus 9. This is really a fairly complicated kind of problem to be hitting you with this early in the techniques chapter. Okay? Let's just say, well, no. This is something you know how to do. I thought that's the same as a division, right? X squared plus 9 into 4x squared. Would you buy that? Okay, we'll do it. Do the division. What does that give you? X squared and 4x squared will go 4 times. And then you multiply, and that gives you 4x squared plus 36. And then you do what? You subtract. These go away. That leaves you a minus 36 over x squared plus 9. Right? So, what this gives you is the integral of 4 minus 36 over x squared minus 9. My 9 looks pretty lousy. And all that times dx. Well, that's the integral of 4 dx, if I could write. Okay. When it doesn't come up, I can't see where I have written and where I haven't. Minus the integral of 36 over x squared plus 9 dx. I think everybody can do the first one, right? What would that be? Integral of 4 dx. 4x, okay? Now the second one is awfully close to what this one is, isn't it? Only it's a 36 here. Well, what we've got then, rather than 4, we got a 36, and we've got a minus in front too. So it's minus 36 thirds, which happens to be 12, times the arctangent or inverse tangent of x over 3. So that would be, what did I say? Minus 12 times the inverse tangent of x over 3, then plus c. Okay. Now, a little bit tricky there, but anytime you have an improper fraction here, which means the degree of the numerator is equal to or greater than the degree of the denominator, and you can't see anything else to do, this is division, long division, and get it into some number plus or minus something that you do have a proper fraction here, and get it down with that. Okay? So I think those are the answers I get. Let's see what they do when they get them. And if I've got something wrong, we'll forget about it and go with theirs, okay? So anyone need that a little bit longer? Okay. So let's see that first one. The arctangent rule, which I didn't know we had an arctangent rule, but that's what it is. That's the same as 4 times the integral of dx over x squared plus 3 squared, which in the book is 3 squared plus x squared. And that is 4 times 1/3 of the arctangent of x over 3 plus c. Just taking it out of the table, you know. I don't know that there was an arctangent rule, or if y'all had it before, I don't think so. And anyway, that's 4/3 arctangent x over 3 plus c. Always for indefinite intervals, remember to put the plus c. The second one, the arctangent rule does not apply to b because the numerator contains a factor of x. Now they say a log rule. Well, the thing is, it's a substitution. And if you do the substitution, let u equal x squared plus 9, du is 2x plus dx, then you have 4x, which is 2 times dx. So pull the 2 outside the integral, and now you have du over u, and that's 2 times the log of absolute value of u plus c. Then go back and plug in the x squared plus 9, which always has to be positive, so you can drop the absolute value of r as 2 times the log x squared plus 9 plus c. Okay. And c, because the degree of the numerator is equal to or if it were greater than the degree of the denominator, first use division to rewrite the improper rational function as the sum of a polynomial and a proper rational function. So that would be, that's what we got to. Integral of 4 dx is real simple. Then pull out the minus 36, and you've got your arctangent again. So it's 4x minus 36 times 1/3 arctangent x over 3 plus c, and that'd be 4 minus 12 arctangent x over 3. That's hitting you awfully hard with some pretty rough little things to do right off the top. Only one of those had a substitution in it. The others you had to look at the table to get. Now, did y'all do arctangent rules earlier? What, derivative arctangents, or did you do integrals? You did do integrals.
I did.
What's that?
In high school, my teacher did.
Oh, okay, right. But I'm talking about in Cal 1. We sure didn't cover them. So it just, for them to say, oh, arctangent rule, log rule, you know, stuff like this, we didn't do them, okay. So, finding integrals to basic integration, integrands to basic integration rules. Here are procedures for finding integrands to basic integration rules. Expand the numerator if that's helpful. Okay, for instance, if you had 1 plus e to the x squared, go on and multiply it out. If it's helpful. I mean, if you can do it without it, you might want to try it without it. Separate the numerator. And this is a pretty good technique too. Anytime this has a plus or minus in it, if you can't see a way to make this fit, then separate it. 1 over this plus that over that, you know? Okay? Complete the square. Okay? All well and good, except they really don't show you how to complete the square there. Though I hope most of you do remember. And that's a pretty serious example, because we've got minus signs and reversed order and all sorts of things there, which that's not obvious. It is the same thing, but they don't say how to do that. So let me show completing the square. Y'all know how to do it, or is this something you're a little fuzzy on? Okay, let's take that denominator, the radicand in the denominator, 2x minus x squared. Now that's not something I would normally think of completing the square, except maybe doing this, minus an x squared minus 2x. Ha! I think I could consider completing a square there. Okay? Well, what would you have to do? I don't know if you remember, that looks a lot like, and this one's so simple, you probably could see, if you put a plus 1 in there, you got it, right? That's a perfect square now, because you can see it. Otherwise, do this. Take half of this, half of negative 2 is negative 1, square it, and you get plus 1. So that completes the square, but that's a different problem, isn't it? Unless, of course, you put a plus 1 on the outside. Now it's the same problem, because this is minus x squared minus 2x minus 1 plus 1 is 0. So yeah, you get the same thing, minus x squared plus 2x. So that is the same thing. All right? Now, that was all under a radical here, so put this back under a radical, except to twist it around some, and put it as the radical of 1 minus, and what is the perfect square of that? What is that the perfect square of? X minus 1 squared. Okay? And that's in the denominator. You had a dx up here. That's now, well, no, you don't have a dx. You just have a 1 there. Sorry. I was putting it in a radical. Okay? Okay. Now, that is the form of the arc sine. Whoa! I hate it when this happens. This chair will grab the cord, and I've almost lost computers that way. Okay? Hopefully that won't grab it anymore. Okay? This is an arc sine where your argument for sine is x minus 1. Okay? Remember, that was a form like right here. du over square root of a squared minus, where your a squared was 1, your u in this case was x minus 1. So arc sine of x minus 1 plus 1. Okay, they didn't take you that far on this, but that's where it was heading. So there's an art even to using a table. You think, oh, well, I'll just look it up on the table. No, you got to get in the same form as the table. And that's what this is doing. This gets it into 1 over the square root of a squared minus u squared. And then go from there. That is it. Now this one, just like the previous one, do your division. Okay? And this happens to be how it comes out, that you have to divide x squared into a. X squared plus 1 into x squared. And you'll see that is what it turns out. This is a simple integration here. This is a inverse tangent. That's the form for inverse tangent. Okay, this one. Okay. This is not nearly as obvious. Okay. It says here, add and subtract terms in the numerator. Okay. And that's what I was starting to do on the last one. I thought that's just going to get a little too involved. And here they go and do it to you on this one. Well, why would that make sense here? Well, by substitution, you see the derivative of this denominator is 2x plus 2. So it'd be nice to have a 2x plus 2 in the numerator, but you don't. But put a 2x plus 2 and then do a minus 2. Then do this one this way, there's a log function. And then minus 2 over this, that's something else. Okay, we haven't gotten to the place where we can do it yet. Oh no, we can do it because this is let this be u and this be 2 over u squared. That's 2u to the minus 2. And you can do that. That's powerful. Okay? So that was all right too. Mostly because that's a perfect square right there. If that wasn't a perfect square, that is a lot bigger pain in the neck or some other part of your anatomy. Okay? Trigonometric identities, and they pulled one of the most obscure ones out, but that sure enough is a trig identity. Now, this is one I was also thinking about with one of the early examples, but it doesn't work as well for that one as it does here. Whenever you have a trig expression like this, a radical expression down here, sum or difference of 2 radicals, and even sometimes when you have the sum or difference of 2 entities here, multiplied by the conjugate. And that's what they're saying here. They're saying Pythagorean conjugate. Fine, any conjugate will work. Sometimes it will, because this gives you 1 minus sine squared, okay, which is cosine squared. Now your numerator gets a little more complicated, but your denominator becomes a monomial, and now you can say this is secant squared minus sine x cosine x, which would be tangent x secant x, okay? And you can integrate both of those. So, in other words, try something, okay? See if you can get the form that you were originally given into a form more like one in the table, okay? That's what they mean, fitting integrands to basic integration rules. Get one that fits the basic integration rule, and then you can go with it. What that was, I'm sorry, I got to talking and completely ignored the fact that they skipped a bunch of examples. So let's go back. They only did example C1, okay? And I should have caught this early. I didn't. Okay, let's do example 2 here. Well, why have I not got example 2? All right, let's try again. Okay. Thought I did that, but it didn't do it. Let's do this one. Evaluate this one. The integral from 0 to 1. What's different about this one? Say again? It's a definite integral, which sometimes are a lot more fun because you can completely ignore 4 minus x squared. Okay. What would be your approach on that one? Anybody have one? A guess, a recommendation, suggestion? What would you do? Hint. Split the numerators. Integral from 0 to 1 of x dx over square root of 4 minus x squared plus 3 times the integral of dx over square root of 4 minus x squared. Is that legal in most states? And that's 0 to 1. Feel okay with that? You see what I did? Oh, I left off the dx there is one thing I did. Yeah. Okay. All right. Split this part over the denominator plus that part over the denominator. Okay? While I was doing it, I just went on and pulled the 3 on the outside, because that looks more like our standard form. Okay, what would be your recommendation here? Some of you said you had this, most of you said you had it. Substitution, okay? And let's substitute, let U be whatever the most complicated, the innermost part of the most complicated part of your problem, which would be what? Let U equal 4 minus x squared. Then always the next step is du is equal to negative 2x dx. Okay? Now, we don't have a negative and we don't have a 2. We just have x dx, so let's divide both of these by negative 2. Okay? These will go out. Now we have a x dx, and that's equal to negative 1/2 du. So to change this one, let's pull the negative 1/2 on the outside. We'll do the integral from, and now this is your du, because we pulled the negative 1/2 on the outside. And what would that be there? Square root of u. Okay? Now the other thing we've got to do, since we changed our variables, we got to change our limits. So we go up here, and when x is 0, what is u? 4. And when x is 1, what is u? 3. Okay? Now, I usually don't like to integrate from 4 to 3. I like to do from 3 to 4. Well, what is required for me to swap those two? Change the sign. And we got a minus on the outside, and I don't really like it there, so it's going to change the sign. This will be 1/2 the integral from 3 to 4. Okay, that took care of the sign change, okay? Now, I don't like radicals particularly. So how could I express that radical in terms of exponents? U to the negative 1/2 du. And now I've got a power function, don't I? And we know how to do that. What would that integral be? Or do we? Okay, we'll come back to that in a second, okay? How about over here? We also got a plus 3. And what does that look like? From our table, anyone say something? Arc sine. It sure looks like an arc sine to me. That's number 18 in the table. Arc sine of x over 2, wouldn't you say? See, in the table it's a squared, which in this place would be 2 squared minus x u squared. We're going to do x squared. That's the arc sine of x over 2. Okay? Okay. And we know we got a plus c out here. So I'll go on and write it down before I forget. No, we don't. No, we don't. No, we don't. Why? It's a definite integral. I forgot that. Okay? I was looking at my table. Going to evaluate that from 0 to 1. Okay, we'll come back and do that in a minute too. Let's go back to our other one. Did you figure out how to integrate this? Okay. It's going to be u to the 1/2 with a 2 in front. And that 2 is going to cancel that 2 out. Oh, nice. And that's evaluated from 3 to 4. Okay? Plus this thing, 3 inverse sine of x over 2 evaluated from 0 to 1. It's strange to have two different limits because we changed variable. Well, what is, if you plug in the 4 for the u, 4 to the 1/2? In other words, square root of 4. 2 minus square root of 3, that's that part, plus, and what's the inverse sine of 1/2? Inverse sine of 1/2. What? Say again? Pi over 2, you said? No, that would be, inverse sine of pi over 2 would be, well, the sine of pi over 2 is 1, not 1/2. The sine of what angle is 1/2? We give you inverse sine. Pi 6, or 30 degrees if you prefer that. So let's do pi 6. And what's the inverse sine of 0? 0. Okay? So there we would have this. So this looks like it's 2 minus root 3 plus pi halves. Weird number, okay? They turned it around, but got the same thing. If you wanted to plug in values, you get them, okay? Now, they have a little blurb there about a midpoint rule. I don't know exactly why they're throwing that in there now, but I guess it's fine to do so. Okay. All right. That used two different rules because you split them up. So let's do example 3. All right, to erase, get out of there. Okay. Example 3. Okay. Here we have an integral of x squared over the square root of 16 minus x to the 6th dx. Boy, in an introduction chapter to techniques of integration, these are some really hairy problems, okay? They're using substitution like crazy here. What would be your approach? And honestly, this takes some tricks to do. Okay? I'm really surprised they would do something. I've taught from this author before. It's the first time I've seen him start off so complicated in a chapter that's really fairly straightforward. But he is really going overboard here. If this were a perfect square down, not a perfect square, had squares in them, and 16 is squared, is the square root of 4. What is that the square of? X cubed. So let's rewrite that first as the integral, and this is an indefinite integral, of x squared dx over the square root of 16 minus x cubed squared. Okay? Anything maybe come to mind now? Second? Minus 1? Okay. Let me show you what comes to my mind. It may be a bad thought, okay? Let's let u equal, what would you think? X cubed. Excellent, okay? Not the innermost part of the most complicated look at the problem, but the innermost part of the most complicated look. Okay. Let that be your x cubed. Then what? What's the next step always? du is equal to 3x squared dx. Okay? We don't want a 3x squared dx. We want x squared dx, so let's divide by 3. Okay? Now we have a du over 3 in the numerator, so let's pull the 1/3 outside and just have the integral of du over the square root of 16 minus u squared. Ding, 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 ding. What does that remind you of? That's the inverse sine function, right? So it would be 1/3. And if you remember how that runs, that would be 1/4, right? Inverse sine of u over 4. Okay? Plus c. But let's go back. We didn't start with u's, so let's not end with u's. So 1/3 of 1/4 is 1/12. The inverse sine of x cubed over 4 plus c. I'm sure hoping that's what they get. 1/3, whoa! Did I do that wrong? Seems like to me they left off a 1/4 somewhere there, didn't they? Doesn't it seem like that way to you? Because the integral of du over a squared plus u squared is 1/a. Oh wait, yeah, square root of a squared minus u squared is arc sine. Oh no, I'm sorry. I was looking at the arc tangent. Sorry about that. There's no 1/4 there. Okay, that's just 1/3. Sorry about that. Have I been messing that up all along? It's just arc sine u over a. Sorry about that. I messed it up. Okay? All right. Example 4. Find the integral of 1/1 plus e to the x dx. All right. Goodness gracious, what are we going to do with that? Right off the top? Second? Okay, that would be something I would want to try. However, I don't see for sure if it's going to help, but let's give it a shot. Okay, multiply by the conjugate. Okay, let's do this off to the side. 1/1 plus e to the x, multiply that by 1 minus e to the x. But if you multiply the denominator by that, you got to multiply the numerator by that too. And what does that give you? Numerator is 1 minus e to the x. Denominator is 1. What? Isn't it that? And frankly, can't see how it helps. Okay? Second? Okay, I wondered about substitution myself. The only thing I could think to substitute was let x equal u, And I don't think that helps us any. Okay? Then we just change our whole problem to 1 over 1 plus e to the u du. And we're no better off. Okay? And like I said, this is really bizarre to get this convoluted a type of problem this early. Okay? Except maybe your substitution is going to work. Well, no. Okay. There's that one other technique, and we already have covered these and we didn't think about it. It said separate the numerator. Okay? Let's try this. So let me erase this part over here because that got us nowhere. It was worth a shot, though. Always worth a shot to try something. Okay? Now, if that numerator was an e to the x, we might be able to do something with it, right? So let's try this. Integrate 1 plus e to the x minus e to the x over 1 plus e to the x. Now that looks a little stupid almost to do, doesn't it? Okay? But what we get now is this over this, which I can do, minus this over this, which I think your substitution could do. So that, I think, is the way to go on this one. Okay? So this will be the integral of 1 plus e to the x over 1 plus e to the x dx. Okay? Minus the integral e to the x over 1 plus e to the x dx, if you can read my writing. What's this one? The first one. 1. Yeah, so that integrates to be x. Okay? Minus, what does that one do? That one, let's try Brandon's substitution. What would you substitute? Let u equal that denominator, 1 plus e to the x. Then, how do you follow that? du is equal to e to the x dx. Hey, there we have an e to the x dx there. So this becomes minus the integral of du over u. And I think we can do that one, can't we? X minus natural log of absolute value of u. And then we can do a plus c if we want. But then we don't like using x's mixed up in there. And since we started with x's, let's leave with x's. It'd be 1 plus the natural log of, and what was our u? 1 plus e to the x plus c. Now, notice I lost my absolute value bar. Why? E to the x is always positive. So 1 plus e to the x is always going to be positive. So sure enough, you can lose the absolute value bar. So that's what that one becomes, I sure hope. Let's see if it does. X minus log of 1 plus e to the x plus c. Very good. Okay. We seem to be losing people like flies, okay? Sorry about that. Any questions? Do I need to leave that up there a little longer? These, and I swear this is so bizarre for them to give this complicated of examples when we haven't even hit any of these techniques yet. I guess this is where we're hitting them, okay? How about this one? Find the integral of cotangent x, that's always a dangerous way to start, times the natural log of sine x dx. Now, I found this a little bizarre in several ways. Okay? One way I find it bizarre is they have the sin x in parentheses, which basically says that x has to be between 0 and pi, not including 0, because you can't take the log of 0, and you can't take the log of 0. X equals 0. So they have to be between there, or some other equivalent thing. So this is a very limited domain here, but they haven't put any limits here, so they haven't indicated that's a limited domain. But let's just assume right from the start it's something inside 0 and pi. It can't be 0 or pi, but anything in between that keeps sin x positive there. Okay. Now, what would be, here's something I would always do. I'm not sure it's going to be helpful, but anytime I've got these other trig functions there, get them in terms of sines and cosines. So that would be the integral of, and what is cotangent u, or x? Right, yeah. What is it? Cosine of x over sine of x. And by the way, time out, if you're between 0 and pi, then your cosine is defined, because cosine of 0, well, let's see, cosine of 0 is not defined, and cosine of pi is not defined, because again you have zeros there. But if you're inside that, then this is defined, and if you're inside that, your log sine is defined. So you've got to be between 0 and pi or some other increment like that. Okay? And then this will be times the log of sine x dx. Okay. With that in mind, what can you do? What would be another first step? Anything come to mind? Anything at all? Substitute what? Okay. So let u equal natural log of sine x. Is that what you said? Okay. Actually, that may be a very good idea. Let's see what happens. Let u equal the natural log of sine x. See, my first inclination would be let u equal sine x, the innermost part. But guess what? It's not going to help you a lot, because derivative of sine x would then be cosine x dx, but you still don't have, no, then I think you'd be, yeah. Second? Yeah. But let's try this then. What's your next step? Then du is equal to 1 over sine x times chain rule, times cosine x, which is dx, which is exactly what we have here. So that is indeed a great substitution. Okay? So now we have the integral of u du, right? And what's that? U squared over 2 plus c, and then plug in what we've got. That would be the natural log of sine x, that's your u, squared over 2 plus c. That should be it. 1/2 they put the 1/2 out front. Natural log of sine x squared. Now, again, if this were Webasine, and they were looking for the 1/2 out here and that there, they say this is the wrong answer. Well, of course it's the right answer, but it wouldn't be in exactly the form they wanted. So they sort of drive me nuts. All right, okay with that one? Let's do example 6 and find this one. The integral of tangent squared x dx. Okay? Now, what might come to mind? Okay, I heard something, but I couldn't make it out.
This is sine and cosine.
Right, it's sine squared over cosine squared. That usually comes to my mind too. The trouble is, in this case, I'm not certain it's going to help, but let's give it a shot. Sine squared x over cosine squared x dx. Okay? Now, what would then be your next step? Well, part of me would say let u be cosine x, and then du would be minus sine x dx, but you still have a sine x up there. Another thing I think that might come to mind is this one. Trig identity. What is tangent squared x? It's a secant squared x minus 1 dx. Okay? What's the integral of secant squared x? Anyone remember? That's tangent x. And what's the integral of dx? X, yeah, I'm sorry. X plus c. So that actually turned out being one of the easier ones. Wait a minute. If I had copied the problem down right, it might have made more sense. It was tangent squared 2x. Sorry about this, folks. Okay. So I'm not sure we're far off. In fact, I think we're probably pretty close. But it does make a difference here. Okay. When I looked at their answer, I thought, where did that come from? And I thought, I didn't copy it down. Okay. Would the same substitution work here? Let's try it. I think so. Integral of secant squared 2x minus 1 dx. Okay? And that would be integral of secant squared 2x minus, or dx minus the integral of dx. I can't write. Okay. Now, what's that antiderivative of that? That would be tangent 2x, okay, divided by 2, okay, because when you chain rule that, okay, minus x plus c, okay, so 1/2 the tangent of 2x minus x plus c. Now they did a different substitution that I'm not even I don't know that's as correct. Okay. No, I see what they did. Substitute u equal 2x, and then tangent square of u would be, yeah, okay. So they did a substitution. If that helps you see it better, perfectly fine to do. We did it, I just didn't write it down that way. Yeah, comes up the same way. Okay, now after they showed all those, that's when they did the integration rules. And I think the way we did it was actually better because we used some of the integration rules when we were doing the ones. But this is the tough way to start a chapter in my mind. These were pretty esoteric, okay, by a long shot, okay. Homework exercises in this group, 8.1, do number 3, okay, do any of the odds 5 through 13, and by the way, 3 is at calcchat.com, and all the odds 5 through 13 are at calcchat.com, but 7's at calcview.com as well. Do any of the odds, sorry about this, goodness gracious, 15 to 45. There's a whole passel and a half of those. They're all at CalcChat. 17's at CalcView. 47 gets into something we do in a differential equations course. And so for my mind, why in the world are we doing it here? I do not know. If you want to play around with that, it is okay to do. Try to do number 49. Where do they get these differential equations? Maybe that, no? To me, again, they're jumping just crazy here. We haven't talked about a differential equation, and here they're doing them. Did they do it somewhere earlier that I forgot about? I don't recall. But let me give you, we got a couple of minutes. In fact, we got several minutes, folks. It's not the end of class yet. Let me tell you what's going on. Number 47 is a slope field. ds dt is a slope at any point s and t, okay? That's your slope. So you can just plug in -1/2 for t, and s is going to be 0. So basically there, you've got your slopes all along the horizontal axis because that's where s is 0, okay? And all your slopes there are, for different values of t, you can figure out what the slopes are. That's what they're doing there. Now, and 49 is doing the same thing, referring back to that. But then, to talk about general solutions to differential equations, I think what that's based on, let me turn back and just see. Yeah, chapter 6 was differential equations. So that's why they're referring to this. I skipped it because, to me, that's in differential equations. So for my suggestion here is just forget about these and you'll get to them when you're in differential equation. But if you want to play with them, let me at least give you this information. Okay? Here's what I would do with this. And dy, this is number 51, dx is equal to e to the x plus 5 squared. Okay? Do it this way. dy, write that as a differential, is equal to e to the x plus 5 squared dx, and then integrate both sides. This gives you y equal, and then use those techniques we just were talking about to try to solve that. Okay? And frankly, for that one, I would square that binomial and then integrate each piece, just for reference. That's what you do on 53 through 55. You don't have to do those, but if you wanted to, you can. Then, evaluating a definite integral, we did one at least like that. Any of the odds, 57 to 71. They're all at Calc Chat. 59 is at Calc View. Do either 73 or 75 or both. They're at Calc Chat. They're not at Calc View. Do either 77 or 79 or both. They're at Calc Chat, not at Calc View. You can think about 81 as much as you'd like or as little as you'd like and move on. 83 is one just finding a constant. You can try that if you'd like. It should be at Calc Chat. 85 is more, talking through a solution than actually doing one, but you can think about that too. 87 I think you can do. 89 looks like you could do. And then any of the odds, 91 is a volume problem, 93 is an arc length problem, and 95 is a surface area problem. Those basically go back to what we just did in Chapter 7. So you should be able to do those. Average value, I don't know if we've run into one like that yet or not, but you can give a look at 97. If you can't get anywhere, don't sweat it too much. 99, again, is the arc length problem like Chapter 7. And then finding patterns is see if you can figure out based on what they're giving you in 101. If you can't, try calcchat.com. It should have it. And 103 is methods of integration, which is what we're going to get to next. So don't get too tied up with that. All right. Now, is there time to start 8.2? Let me at least introduce you to it. Okay? So let's get out of this. Okay? I don't know why everybody's leaving today. Is there something special going on or something? Okay, 8.2. And we'll get going on this big time next time. All right. Wait. Hitting the wrong keys here. From current slide. I'm getting awfully hungry. I think I'm losing track. Okay, integration techniques and improper integrals. This we finally, well, that first section hit some integration techniques, but boy, did it have a bunch of variety of things to do with that. Now we're going to be very much more specific and talk about one technique called integration by parts. The objective here is to find an antiderivative using integration by parts. And basically this is based on the been sitting too long. Product rule. This section we will study an important integration technique called integration by parts. This technique can be applied to a wide variety of functions. Is particularly useful for integrands involving products of algebraic and transcendental functions. For instance, integration by parts works well with integrals such as this. Algebraic part or polynomial part, transcendental part. Algebraic or polynomial part, transcendental part. Transcendental part, okay? I guess sign is transcendental, but that's trig and transcendental, okay? So we're going to find out those work really well with integration by parts. But they haven't told us what that is yet. So let's get the idea. Integration by parts is based on the formula for the derivative of a product. That if you have d by dx of a product of two functions that are both integrable, u times v, you tell me what that is. Refresher from Cal 1. Derivative of a product.
First times the derivative of the
First times derivative of the second,
second times the derivative.
plus the second times derivative of the first. Exactly. You were reading this, weren't you? Okay.
I wasn't.
No, you aren't. Okay. All right. Or you can write it uv prime plus vu prime. Actually, I like it more in differential form. D of uv is u dv plus v du. You know, like that. Okay. Now, both of these have to be differentiable functions. And all those that we gave in the example before were. What are we going to do with this is subtract. When u and v are both continuous, u prime and v prime are both continuous, you can integrate both sides like this. Okay, let's go back here. And this is a perfect derivative of uv. So if you integrate this, again, I'd write it in differential form. duv is equal to u dv plus v du. Okay, just leave off the dx's here. Integrate this, you get uv. Integrate this, you get the integral of u dv. Integrate this, you get the integral of v du. Okay? Or just take the integral of that. So that's what we're talking about here. uv is the integral of uv prime plus the integral of the u prime. Okay? Or, as I said, the integral of u dv plus integral of v du. Now, so what? That hasn't helped us do anything. But if you take this one, subtract this from both sides, then you get this. The integral of u dv is uv minus the integral of v du. Okay? How does that help us then? Well, here's the deal. If this integral that you happen to have is a product that you see no way in the world to integrate, okay? But you can imagine this, let u, I hate to use u and v here because I like to use this for my substitution. If you can break it into a part that's a function times the derivative of another function, then if you can integrate this part without making it any worse, and differentiate this part without making it any worse, then the integral of this times this will be your first part. You don't have to integrate anymore. That's outside the integral. Minus the integral, and if we integrated this and got something a little simpler, differentiated this and didn't get anything any worse, then maybe you can integrate that one. And if you can, you've got that done. Okay? So that's going to be our technique. That's where we're going to go. And we'll begin next time with these guidelines. Okay? Right there on page 523. Thank you, folks, for staying around the full time. The few, the proud. Okay? And we'll pick up there. Oh, and I gave you your test, right? Yeah. All right. Good deal.